get the recording started up. All right, all right. And let's just hop into it and start talking about static equilibrium and stuff like that. So, first thing I want to know is what's the difference between a force and a torque again? So, throw back the last few classes.
Torque is, torque is rotational force.
Yeah, pretty much. Yeah, a torque is essentially just a rotational force. And how do we actually calculate a torque?
Uh, isn't it perpendicular force? It's the force. So like if a force is coming at an angle, you have to calculate the force that's perpendicular to the line of uh, like the radius, but like there's a certain word for it.
What if it's not exactly perpendicular? Is there a more general equation for calculating the torque?
Is it like F sine radius?
Could you repeat that?
At like the force sine the angle that it's applied at times the radius.
Times the sine of the angle. Yep. And how do where do we get that sine of the angle from?
In between the horizontal and the force that it's applied at. If that makes sense. Like from the horizontal to the angle of force.
Mm-hmm. And more specifically, what is the original equation that we actually get the sine theta from? Like, I want the vector form of the torque. Sine theta is how we get the magnitude.
So, what is the question?
So, what is the most general form for the equation of torque?
It goes the radius times the force.
Not times the force. It's a type of multiplication.
Oh, is it so it's vector multiplication, but it's not. It's not dot. Is it dot product?
No, it's not a dot product. It's the other it's the other type.
I forget what the name for the other type is.
It's called the cross product.
Cross product.
Yep. So it's r, which is our you mentioned it's sort of like a radius. It's like a
Yeah.
distance from the point that we want to calculate the torque at. R cross the force. R cross F. So how do we find the direction of the torque? If we know the direction of R and the direction of F.
Um, it would be it would be the direction of the force because they're all going in the same direction. So whatever direction the force is in will be the direction of the torque. If you're doing net torque, then it's the direction of the net force.
It wouldn't be the direction of the force because the cross product. What direction is the cross product relative to the other two vectors?
Is it more it's not the direction of the force, but it's like is it like a 45-degree angle to the
Not
force?
not a 45 degree.
What um
Perpendicular?
Perpendicular. The the torque is always perpendicular to both R and F. So for example, if R is out to the right and the force is straight upward, R F, the torque is going to be perpendicular to both of these. So there's two options for the direction of the torque. What are they?
um, left and down.
Left and down are not perpendicular to both of these.
It's in or out.
Exactly, in or out of the page. And so, what direction would it be in for this example? How would we find the direction of the torque?
Wouldn't we just draw a line from the end of R to the tip of F?
What do you mean by that?
Like, isn't that what the... I don't know, that's vector addition. So,
So we know that the torque is either in or out of the page. He hasn't really covered the right-hand rule too much in this class, but he's at least on this, right?
not sure. It's why I came.
Yeah. So the torque in this example, the way you find the direction of the torque is you use the right-hand rule. So you point your fingers, essentially you point your pointer finger in the direction of R, so to the right, and then you point your palm in the direction of the force. So your fingers are pointed to the right, and your palm should be straight up towards the ceiling. What direction is your thumb in?
It's pointing out at you in the Z direction.
Yeah, exactly. It's out of the page. So the torque is coming out of the page, like I guess we'll draw it like this. So this little dot means out of the page. And then to find the direction that the torque is going to rotate, you stick your thumb in the direction of the torque, and then curl your fingers around it. Your fingers are going to curl counterclockwise, which makes sense, right? You pull upwards on, if this was like a beam,
Yeah.
you pull upwards, it's going to want to rotate around like this. Pretty simple. So that's a torque. It's pretty simple. It's just a rotational force. And so all of these examples that you're going to see, you saw in class yesterday and on your flip it and on the quiz tomorrow, has to do with static equilibrium. What conditions do we need to have met for static equilibrium to occur?
Net force needs to be 0.
Mm-hmm. And what else?
And net torque needs to be 0.
Exactly. Net force, so F net is equal to 0. And the total sum of the torque also has to equal 0 for the entire system. That's pretty much it. And at this point, I mean, there's not really any other concepts to go over. It's all just working through practice problems. Does anyone have any questions before we want to hop into some practice problems? All right, then. Let's hop into it. So, let's go ahead and have a 50 kilo block of steel, and we're going to go ahead and hang it from the end of a 10 meter long massless beam. So the beam is hanging out here. It's 10 meters long. And we have this big ol' block of steel hanging from the end of it. And we're going to go ahead and have a rope attached to the beam 3 meters out and connected to a wall. So this here is our rope. This is our beam. This is our wall. And this is the steel block. We have 3 meter length here, and the total length of the entire beam is 10 meters. So first thing we want to do is we want to go ahead and draw and visualize all of the forces and torques acting on the beam. And then we want to find what would the tension on the rope be if the system is in equilibrium. Let's take 10 minutes, then we'll go over this.
Alright, so we're trying to find all the forces and what's the tension.
Yeah. Our goal is to find the tension in the rope here. All right, so let's go ahead and go over this. So, first thing we want to do is draw all of the forces and torques acting on the beam. Let's start out. For forces, there's going to be potentially 3 spots where there's potentially going to be some sort of force acting on the beam. What are those 3 spots?
There's the weight of the beam, correct?
What was that?
The weight of the beam.
We're assuming the beam is massless, so we're not worried about that.
Alright. Is there the weight of? Is there like a force that is applied, like at the corner, like near the wall?
Like right here?
Yeah, exactly.
Mm-hmm. Yeah, there's probably a force acting there.
I don't want to say that it's a. I want to say that it's a tension force, but
Right here on the wall?
yeah, but it's not. It's just a force between the wall.
Yeah, it's
The
just a
normal force?
yeah, it's just some sort of a force. There's going to be a normal force, which what direction would the normal force between the beam and the wall be?
Should be just left, correct?
On the beam, so the wall is pulling on the beam.
Yeah, I want to be.
Towards the beam?
Hmm?
Should it be towards the beam?
Yeah, exactly. So there's going to be some sort of a normal force acting to the right on the beam. So we have that's in the x direction. So we know the total Fx is equal to our normal force acting to the right. Is there any other force acting at that point? Any force in the y direction?
The y direction or the x direction?
In the y direction at this point. I mean, there might be.
There's a hinge force, basically, since there's got to be some sort of force that is like point. I want to say like going more at like a 45-degree angle from that point to the right, like a hinge force almost.
What, like this?
Yeah.
That would be the total force acting at that point, but it's going to be a combination of the normal force acting to the right, and there's probably, might not, there might be some sort of a frictional force acting upward.
Okay.
So we'll add that in. We'll have some sort of a friction. So Fy is equal to, we might have some sort of a frictional force acting between the beam and the wall. So then there's going to be 2 other spots where there's going to be some sort of force acting on the beam.
Tension of the rope.
Exactly. The tension in the rope. So it's right here. And so what angle does the rope make with the beam?
45 degrees.
45 degrees. So if the tension in the rope, which is acting along in the direction of the rope, can just be broken into x and y components, right?
Yeah.
So we can just write it as, it would be in the negative x direction because it's off to the left, minus t times the cosine of 45. What's the cosine of 45?
Cosine of 45 is, I want to say,
2.
What was that, Alicia?
Is it 2 square root 2?
2 times square root of 2?
Or 2 times square root of 2? I forgot. Sorry.
It's the square root of 2 over 2. Yeah. You were close. You had the right idea that it involved 2 and the square root of 2. It's the square root of 2 over 2. And then we also had that same exact tension in the positive y direction. The same magnitude of the tension. Plus t root 2 over 2. And then we have one more spot where there's a force acting on the beam.
the weight force of the block. I don't know if that's a in between it.
Yeah, the force of the block, the weight of the block. And that's all in the y direction. And it's in the negative y direction, so it's going to be mg. And for equilibrium, we know that both of these have to be 0. Is this enough to solve for our tension?
Well, not sure.
We do need the torque.
Exactly. This isn't enough information to solve for our tension in the rope, because the main thing is we don't know what the hell's going on with this frictional force or the normal force. We just don't know what they are. So we need to also take into account the torques, because we know the total torque, the sum of all torques at any point on this beam is going to be 0. So how do we go ahead and calculate the torque at a point?
You calculate the force at that point and the radius and the cross product.
The force and the radius. So we have to select some sort of a pivot point to actually calculate our torque, right?
Yeah.
Where would we want to put our pivot point here? What's the most convenient spot?
Probably where the frictional force, like in the corner with the rope.
Right here where the beam meets the wall?
Yeah.
Why is that?
Because you can eliminate the frictional force there. I mean, frictional force would be 0, so you can find everything else, I guess.
Yeah, there's no torque from the frictional force or the normal force here, because the distance from our pivot point to those forces is 0. R cross F, if R is 0, the torque is 0. So let's go ahead and calculate our torque, our total torque at our selected pivot point. And we don't have to worry about the friction or the normal force. So what is contributing to the torque here?
Tension?
Tension, sure thing. And so what would the torque here be from the tension?
How many Counterclockwise would be positive, right?
Positive. Mm-hmm.
So it would be positive 3 times the tension force
Mm-hmm. Anything
times
else?
sine of theta.
Yep, sine of theta. And what's the angle between the tension and our vector, or r vector, out to here?
Oh, 45.
Yep. Or in this case, will technically be 135 degrees, but same thing. Yep, so we have sine of 45 degrees, and what is that?
Oh, square root of 2 over 2.
Exactly. So 3 root 2 over 2 tension. And then what else contributes to the torque here?
The block.
The block. Yep. What would be the torque here due to the block?
The length is 10 meters, so either 10
Mm-hmm.
divided by the weight of the block, which is 50 kilograms, and then times 10 for gravity.
So 10 mg. And is it positive or negative?
That would be negative.
Yep, negative because it's clockwise. And we know that has to go ahead and equal 0. And let me actually go ahead and rewrite it. Instead of the numbers, I'm going to use D and L, where D is just 3 meters and L is the total length. Is this enough information to go ahead and solve for our tension?
Yes.
Yes. Why is it enough? How many unknowns do we have here? Let's see. We know what M is. What was that?
Oh, we have 2?
We have 2 unknowns. What are they?
Oh wait, I guess technically 3. It would be tension, the normal force, and the friction force, but we have 3 equations, so it should be fine.
Exactly. We have 3 equations and 3 unknowns, which is enough information to solve everything in this entire problem. So we actually don't even need these first 2 equations. We only need the torque equation to solve for the tension itself. But we can use all 3 to calculate also the normal force and the frictional force. And let's do that. Why not? Bonus points. We'll calculate all the forces. So, what's the first thing we can do?
You could.
We could start off with the torque of the tension force, so we would just plug things in.
Yep.
Or I guess first we would move the block to the other side, and then we would plug things in.
Yep. So let's do root 2 over 2 dt is equal to lmg. We just moved this over to the right side, and then we can just solve for t. T is equal to 2 lmg over root 2 dt. Plug everything into a calculator. Did anyone calculate a value? 2 times 10 meters times 50 kilos times g equals 10 over square root of 2 times d is 3 meters. Oh, I realized I did a dumb. I did a dumb. What was that?
I got a 2357.
Yep, 2357. It's equal to, I'm just going to round it to about 20, so 2.4 kilonewtons. Right, it would be 2357 newtons, because we've kept everything else in SI units, kilograms, meters, what else? So we should get newtons, and then I'm just being lazy and just writing kilonewtons. So now, how would we go ahead and calculate the frictional force and the normal force?
You could just plug that tension back into the FX equation.
Yeah, sure. So
Tension back into the FY equation too, and you'd get the answer pretty quickly.
yep, exactly. So we know the normal force from the FX equation is equal to tension times root 2 over 2. We just move t root 2 over 2 to the right side. And so we get a normal force of about 1.7 kilonewtons. Obviously, I'm just rounding a lot and being lazy. And then for the Fy equation, we can solve for the frictional force. We know F is equal to big mg minus t root 2 over 2. Just moved all this stuff to the right side, which is equal to 50 times g minus t root 2 over 2, which is the same thing as the normal force. We have a frictional force of negative 1.2 kilonewtons. So we got a negative value here. Is that a problem?
Yeah, because the frictional force is, but actually, it shouldn't be a problem because the frictional force be technically clockwise.
What was that? You're like cutting in and out.
Would the frictional force be clockwise? So it would technically be negative.
It's a force, not a torque.
Oh, okay, cool. So it is a problem that it's negative because the force is in the direction, is in the positive y direction.
But did we know for a fact that it was in the positive y direction?
No.
No, we didn't know. We didn't know if there's a frictional force at all. We just sort of guessed, oh, there might be some sort of frictional force in the positive y direction. And then we solved everything out and we did the math, and then, oh no, the frictional force, we got a negative value. That's not a problem. It just means the force is actually in the negative y direction. That's it. If you calculate everything and you get a negative value, usually just means that you guessed wrong initially by saying it was in the positive y direction, and it's actually in the negative y direction. Anyone have any questions about this? All right. Then you guys should be experts on this.
Oh.
12 out of 12 tomorrow?
Need it.
You need it. All right, let's go ahead and hop into another example. And I think you guys actually, I believe he went over an example very similar to this in class. So it should be similar to what you do, a bit more comfortable with what you guys saw. And also, I like this problem. So we're going to go ahead and have a 5-meter long, 20-kilogram ladder leaned up against a frictionless wall. And the ladder is going to make an angle theta with respect to the wall. So let's go ahead and visualize. We have a wall, and we'll also have the ground. And we have our ladder here. It's going to make an angle of theta with respect to the wall. So, assuming the ladder is at rest, let's go ahead and draw all the forces and torques acting on the ladder. Let's take 5 minutes and then we'll talk about it. All right, so we have our ladder leaning up against our frictionless wall, and the ladder is making an angle theta with respect to the wall. So what are all of the forces acting on our ladder? Just 3 spots where there's going to be forces acting on the ladder.
There's the weight force of the ladder.
Where is that going to act on it?
Center of mass.
Center of mass, and which we'll assume it's a sturdily, evenly constructed ladder, so we'll assume it's at the middle. So we have Fx, it's not in the x direction, y direction is equal to negative mg. What else?
You have the frictional force.
Acting where?
On the ground.
On the ground.
To the left.
To the left?
To the negative x direction. That's
Negative x direction. Let's go ahead and so we'll have negative f. We'll just call it negative f. What else?
The force of the wall against the low in the positive x direction at the top of the ladder.
Sorry, what was that?
The force of the wall against the ladder in the positive x direction at the top of the ladder.
I think your Discord just hates you, but you got through that time. It sounded like the force of the wall on the ladder, and it was like cutting out. But so we have a normal force acting on the wall, acting on the ladder from the wall. We'll call it plus N1. Is there any other forces acting on our ladder?
The floor acting on the ladder going upwards.
Where?
At the same place where the friction force is.
Yep, exactly. We have another normal force acting on the ladder. We'll call it N2. And we know both of these have to equal 0. Right? Now what about torques? How could we... There's going to be one spot on here that's probably going to be easier to deal with in terms of calculating the total net torque on the ladder. What's the most convenient place to choose our pivot point?
Is it where the ladder touches the ground?
Yep. Why is that?
Because that would make both the friction force and the normal force there 0.
Exactly. Makes it super easy because, essentially you usually want to choose your pivot point to be the point where the most forces are occurring, if there's more than one force occurring at that point, because then you can just ignore them and we only have to worry about these other 2 forces. So, what is the torque acting on that point based on the other two forces? What's the torque acting from the weight of the ladder itself?
Be positive, positive L over 2 times the weight.
Mm-hmm. Anything else?
Perpendicular to the force is going straight down, so it should just be that, right?
And you're using L. L is the length of the ladder, right?
Oh, yes.
So we don't have to worry about anything else? Just L over 2 times mg?
Oh, it's supposed to be horizontal, so we would have to do cosine theta.
Cosine of theta?
Yeah. Oh, yeah, it would always be sine of theta.
Yeah, it's going to be sine of theta here. In this case, this is going to be L over 2 mg times the sine, not the sim. Sine of theta, where theta is the angle between our r vector, which goes out along here, and our force vector, which, as you can see, you draw that theta, is the same exact theta that we have up here.
Wait, so why, if you won't mind me asking, why is it L over 2?
Because it's half the length of the ladder. Because
Is that, yeah. So like why? But like why was it half the length of the ladder?
Because that's where the weight of the ladder acts. It acts at the center of mass, which is halfway up the ladder.
Okay.
And then what else? What's the torque due to the normal force on the wall?
It'd just be L times the normal force.
Is it positive or negative?
It would be negative.
So we have negative L times that normal force, N1, times the sine of the angle between them. What would be the angle between them?
Oh, that would also, wait, that would be 90 minus theta.
90 minus theta, so what's there another way of saying 90 minus theta?
We usually use alpha, right?
Yep, so if we have the sine of 90 minus theta.
Oh, cosine theta?
Yeah, cosine theta. Another way we can think of it is we want to know the total, I mean, for the first one, we want to know the total distance here along the floor between the pivot point and the force straight downward. And that would be L over 2 times the sine of theta, because, or it'd be L sine theta over 2, because sine theta would be this length along here, and it would just be half of it. And for this case, we want the height here between the pivot point and the horizontal force, which would be L cosine theta. And we know that total torque has to equal 0. So now, if the coefficient of friction between the ladder and the ground is 0.5, what would be the max angle that our ladder could make with respect to the wall without slipping? It'll take 5 minutes, then we'll go over it. And also, actually, let's go over B and C. So, if the coefficient is 0.5, what's the max angle the ladder can make? And then also, if the ladder were to slip at 40 degrees, what would be the coefficient of friction? Take 5 minutes, then we'll go over it. All right. So we want to know, first of all, if we're given the coefficient of friction, how can we find the max angle the ladder can make before slipping? How could we do this? Well, first of all, we want to be able to find we want to be able to find the absolute limits. We want to find where the frictional force is reaching its limit to where it can no longer stop the ladder from slipping. The first thing we want to do is, how can we relate the frictional force to one of these other forces we have here?
Friction force. I want to say it has to equal the force. It has to be and I think you have to relate it to the normal force on the ground, normal tube, correct?
Yeah, exactly. We have to relate it to the normal force acting on the ground here. How do we do that? Isn't it just mu s times the normal force?
Yeah.
Yeah. And that would be N2. And how can we relate N2 to another force here?
It would be related to the weight of the ladder.
Yep, exactly. And we see here from our y direction equation, N2 is just equal to mg. So we have mu s mg, which we know that this frictional force has to equal the normal force, N1, acting on the wall, from the wall. So now, let's go ahead and plug this into the torque equation and see what happens. So we have L over 2 mg sine theta is equal to, we're going to move this part over to the right side, is equal to L n1, so we'll plug in mu s mg cosine theta. Now, we have a way to, first of all, we can cancel out mg and L on both sides. And now we can solve for mu in terms of theta, or theta in terms of mu. So for B, we want to find theta in terms of mu. So we'll have sine over cosine. So we have tangent theta is equal to 2 mu s. So then theta is equal to the arctangent of 2 mu s, which is just the arctangent of 1. What would that make theta be?
45 degrees.
45 degrees? Yep, 45 degrees. And we can double check. Oh, not a tan of 45 of 1 gives us an angle of 45 degrees. Now, what if we want to go the other way? We're given the fact that it slips at 40 degrees. What would the coefficient be?
Would be 1/2 of the tangent theta.
Yep, just half tangent of theta, or tangent, so 0.5 tangent of 40 degrees. We get a mu of about 0.42. For B, C. We'll put A up here. So now, did anyone have any questions about this?
No, that makes sense.
All right. So now, if we were to take that coefficient from part C, and we're going to place the ladder at an angle of 30 degrees. How far up the ladder could a 100 kilogram person climb before the ladder slips? So, what would change about this situation from the original situation?
Fx would change.
What was that?
Our forces on the x direction would change.
How so?
When a 100 kilogram person starts climbing up, their weight would start pushing downwards
Yep.
onto the ladder.
So let's say we're just going to choose a random spot. Let's say right here. So how would that change the x equation?
We would have m2 minus the weight of the ladder minus the weight of the person.
You mean the y equation?
Oh, yeah, that's the y.
So
my bad.
Yeah, I was confused there. I was like, I think she knows what she's talking about, but she's saying x, and yeah, the x equation doesn't change. But so now, what we have to take into consideration is Fy is equal to N2 minus, we'll call it M plus M, G, is equal to 0, where little m is the weight of the ladder, 20 kilos, and big M is the weight of the person, 100 kilos. And then from there, I mean, we can go ahead and sort of do the same process as before, right? Where we can solve for, we have the frictional force is still equal to mu s n2, which is equal to mu s big M plus little m, g, which is equal to n1. So we have n1 is equal to mu s m plus m g. And then we can go ahead and plug it into the torque equation. So we have same thing, L over 2 mg sine theta is equal to, we actually need to take into account the torque from our new force in the y direction, right?
Oh,
What direction is the torque going to be in?
positive direction?
Positive direction, so it's going to be, so we'll write down torque is equal to L over 2 mg sine theta plus, we'll call it a distance x along the ladder that we'll solve for, plus x big mg sine theta. And that's the torque from our 100 kilo person. And then we have minus L n1 cosine theta is equal to 0. And then we plug in n1. So we have x mg sine theta is equal to, I'm going to move the ln1 cosine theta and L over 2 mg sine theta over to the opposite side. Is equal to L mu s n plus m g cosine theta. Running out of room on the side. Let me actually just go ahead and expand it. There we go. Mg cosine theta minus L over 2 mg sine theta. And then we just solve for x, right? We just divide by big mg sine theta, and we can solve for x. And so if we go ahead and plug everything in, we have mu times L, which was 5 meters, times big M plus little m, 20 kilos plus 100 kilos, 120, times g, which is 10, times the cosine of theta. Theta is 30 degrees. What's the cosine of theta?
Square root of 3 over 2.
Yep, root 3 over 2. And then we have minus L over 2, which is 5 over 2, 2.5, times M times G times the sine of theta. What's the sine of 30 degrees?
1/2.
Yep, 1/2. And then we have to take all of this and divide it by big M G. So 1 big M times G times the sine of theta, which once again is 0.5. And plug everything in. And we find that our 100 kilo person could actually climb about 3.86 meters. So actually quite a bit further up, you know, almost to about here, before the ladder actually slips and they fall down and break their wrist. Anyone have any questions about this?
This looks like a lot. But it makes
Yeah.
sense.
Yeah, it's honestly, it's just writing down the equations, and then it's just algebra.
Yeah.
And if he gives you a problem like this on the quiz tomorrow, this is going to be the majority of the quiz. Like, this problem would be worth 6 or 8 points alone. because I don't think he would expect you to work on this yourself in less than 15 minutes, 20 minutes. So honestly, tomorrow's quiz isn't too... The concepts aren't too difficult. It's just Fx is equal to 0, Fy is equal to 0, torque is equal to 0. Where do you select your pivot point for the torque?
You select it where you can cancel out a force, right?
Yeah, you select it where you can simplify it the most by canceling the most forces. So for the ladder, you select it on the floor where there's 2 forces. For the beam, you select it on the wall where there's 2 forces. Wherever you can cancel out the most forces and only worry about, 1 or 2 forces creating the torque. So you select your pivot point, torque at that point is equal to 0, and then Fx equals 0, Fy equals 0, and then it's just algebra. And it's usually not super complicated algebra.
I just asked a question. For negative L and 1 cosine theta, why was it the whole entire length of the instead of L over 2?
So for L over 2 was for the weight of the ladder, where we go halfway up. And we use the full length L because we're going all the way up the ladder to where it touches the wall. Because the normal force is acting on the top part of the ladder here.
But torque.
What was that?
So I'm more in the X. So torque, it doesn't matter. Like torque. What I'm just getting a little confused about is that torque equation has is all the torque moving in the same direction there, or because L2 mg sine theta is moving, I guess you would say, like out of the page.
Right? Yep, out of the page, so counterclockwise.
Counterclockwise, and then ln is moving into the page.
Yep, into the page. Clockwise. So they end up canceling each other out. Alright. If that's it, I'm going to go ahead and wrap up the session here. Hopefully it helped out a bit. Once again, just Fx is equal to 0, Fy is equal to 0, torque is equal to 0, algebra. That's all tomorrow's quiz is going to be. So, good luck studying. And same time on Thursday, covering tomorrow's material. Thanks, guys, for coming.
Thank you.
All right. Bye.